All right, welcome to AP Chemistry. It's good to have you here. We are on Unit 1.4, and on Unit 1.4, we are looking at composition of pure substances. You see that term, pure substances. And so that means it is made up of one form, all right? So our learning objective here is to explain the quantitative relationship between the elemental composition by mass and the empirical formula of a pure substance. The reason we're focusing on pure substance in the next in unit I think this is unit 1.3. Did I just say 1.4? Yeah. It's unit 1.3, and in unit 1.4 we are going to talk about substances that are not pure. All right, and looking at that. But in 1.3, we're looking at pure substances, and we're taking a relationship between that composition and the empirical formula. So a question might be, how is percent composition by mass calculated? So we need to look at how do we determine the percent composition of a substance. And this is a big deal when we're talking about empirical formulas or pure substances, because once we have the chemical formula of a compound and we have a pure sample of that compound, the ratio of the atoms that make up that compound does not change. You see that? It will remain constant. Now, if a substance is not pure, then we will see variation from the percent composition of all of those elements, right? And so it makes a big difference, and that's one way we can determine the purity of a substance. And so this is the beginning of this. We look at percent composition by mass, and so it says to show an example of problem of percent composite or percent mass calculation. So when we get percent mass, what we're actually doing is we're taking, so let's say percent mass. We're going to say mass of element over total mass times 100%. That's how we get that. All right. So that's going to be our formula. Now, if we look at something like lithium phosphide, and we know that's just the name given, we're not given the formula. Now, funny enough, in AP chemistry, they don't necessarily focus on chemical nomenclature, which is a really good thing because it's kind of tough for people. You may say, well, why did we go over it in honors? We went over in honors because there are some people that don't take AP chemistry, right? And they are then going to take college chemistry. And it's most certainly covered in Gen Chem 1, without a doubt. It's a big portion of it. And it would be egregious to leave them, to let anyone leave my class unprepared, right? Also, it's not a bad thing for you to know. While many of you, with passing the AP exam, will get out of Chem 1 and Chem 2, you may, depending on your major, you may have to go to organic chemistry. And guess what they have in organic chemistry? Chemical nomenclature. But it's a whole different type of nomenclature. It's centered around organic molecules. Radically different from what you learned. If you think what we learned there was difficult, you don't know anything. All right, it's way more complicated. All right, so naming compounds is a part of chemistry, whether you're in Chem 1 or Chem 2 or organic. All right, so looking at that, let's take a look at an example problem. So we have lithium phosphide, and we have, with lithium, we should know, I'm going back a little bit, lithium is a metal. All right, and what do we know about metals? What type of ions do they form? Form cations. And what do we know about cations? They are positive. All right, and then we have sulfur. And we should know from looking at our periodic table where we see metals, where we know where metals are located, where metalloids are located, and where nonmetals are located, right? We should know that. So we should know sulfur is in a region where we see nonmetals, all right? And nonmetals tend to form anions, a negative ion. That's a negative charge, all right? And so we obviously already went through in our first course in honors chemistry or whatever course you just took as a prerequisite for this for AP. You should know that you can tell the number of valence electrons by looking at the group, and then you should be able to tell metals they form cations by doing what? Losing electrons, how many electrons they would lose, and then you should be able to predict the charge of the cation or anion, right? In that case, it would be a cation. Or if you're looking at a nonmetal, you should be able to look at the number of valence electrons, how many electrons it's going to gain to achieve the what? Noble gas configuration, or what we call the octet, right? I mean, 8 electrons in its highest energy level, right? And so we look at those for lithium. We should be able to tell that lithium is in group 1, has 1 valence electron. When it loses that 1 valence electron, it's going to form a 1+ charge. And then when we have phosphorus, why did I put sulfur? No one's correcting me. That's phosphorus, but it's still true. The rest of it's still true. No one says anything. All right. Lithium, 1+, but phosphorus, it's still a nonmetal. It still forms an anion, but it's in group 5. It has 5 valence electrons, and so it would need to gain 3 to achieve a noble gas configuration, so it has a 3- charge. In order for the sum of the charges to equal 0, we need 3 lithium ions for every 1 phosphide ion. Do you see that? And so our formula unit for lithium phosphide is Li3P, right? Or if you remember using the cross technique, and I'm not really doing this for students that I had last year. I'm doing this for students that were not in my class last year because I don't know what you know and what you don't know. So that's what that's for. But you should have learned that last year for sure. Now it comes down to we know the formula unit of lithium phosphide. Now let's show the percent mass of lithium and the percent of mass of phosphorus. Now we can do this by assuming any sample size. All right, we can assume any sample size because in a pure substance, I can't make this clear enough. In a pure substance, the mass ratio of lithium to phosphorus is going to always be the same. Did you hear me say that already? It's going to always be the same. So why would we not just go ahead and assume that we have 1 mole of lithium phosphide? Do you see that? And if we do that, basically right now, all we need to do is calculate the molar mass. Now, who finds that to be a difficult task? Nobody should find that to be a difficult task, especially when given the formula. So we take lithium, and how many lithium do we have in lithium phosphide? 3 moles of lithium. And then we know that lithium has, is that right? Yeah, 3 moles of lithium. And we know that 1 mole of lithium is equal to what mass? 6 point, no, to what mass? 6 point, I want everyone looking at their AP periodic table. I don't want you looking at that. I'm about to take that off the wall. Look at your AP. What does it say? 6.94 grams of lithium. It's not that it's wrong, but I want you to get in the habit of looking at that. All right. So notice I'm using dimensional analysis in this setup. I start with a given, and the given has a unit, and then I am going from 1 unit to another unit. We should never have 2 units in the denominator or 2 units in the numerator. We should have 1 unit Each time we are relating moles to mass. Now, why does this work? This works because what we have here, 6.94 grams, is equal to 1 mole of lithium. And because those values are equal, that expression is equal to 1. So when we multiply 3 moles by this value, we're going to get that value in grams. Do you see that? It doesn't change because this expression is 1. We have a conversion factor. It's a ratio of equivalent values. All right, we're going to pause for a quick second. Okay, so we make our calculation here, and we see that we get 20.82 grams of lithium, right? Again, 3 moles is equal, that's why there's an equal sign there, it's not by accident, is equal to 20.82 grams because we are not changing the value when we multiply by 1. Do you see that? That's the entire concept there. This is why we use dimensional analysis. Dimensional analysis uses conversion factors. I need to see conversion factors. Now, there are times when you are asked to show your setup on your free response of your test. They don't care about your answer. Do you understand? This is why weird math doesn't work there. They only care about your setup. And I'm telling you how to get those points. All right. By the way, they're easy. All right, they're easy. You should be doing it every day. We're gonna master that. All right, the next part. What are we gonna do? Phosphorus. And how many moles of phosphorus do we have in lithium phosphide? 1 mole. And then what's our molar mass? And this is a phosphorus. 1 mole of phosphorus is equal to what? 30.97 grams of phosphorus. Notice I put unit and substance in a dimensional analysis. They say grams, and the substance, grams of lithium, moles of lithium. Except for right there. Now I fixed it. And moles of phosphorus, grams of phosphorus. All right. And so, by the way, I'll do this math. You don't need to get your calculator out. I'll do this one for you because I'm gifted at multiplying by 1. It's just it's my gift. But I can't add to save my life. So y'all tell me what the molar mass of lithium phosphide is. Say again? Anyone disagree? Well, we have all these calculators in here. We should have agreement. I agree with you, but we're all good? 51.79. Okay, well, there you go. Lithium phosphate. Are we on agreement? All right, Li3P. Now, when we get the percent, no one should feel bad about putting an answer out. You should never feel bad about that. You should feel bad if you didn't. You should feel bad if you are just waiting on other people to put stuff out. Then you should feel bad. You should feel real bad. All right? But no, if you call out the wrong answer, good for you for trying. Thank you. Thank you. So now we go to our formula and we see percent mass is going to be the mass of the element that we're looking for over the total mass. Do you see that? So we need to find the percent mass of lithium. So what are we going to do? We're going to take 20.82 grams of lithium over the total mass, which is what? 51.79 grams. And we're going to multiply by 100%. And this will give us, I don't know what I just did there, 100%. And then we should get our percentage. What does that come out to be? Someone said 40.2 in the morning class. Y'all are saying it's 40.2, 40.3? Is that right? Everyone get the same thing? $40.2. All right, so we have 40.2%. All right, so 40.2%. Now, we know it's 40.2%. Do we need to do that same calculation Do we need to do that same calculation in order to find the percent of phosphorus? No, we could just take 100 minus 40.2 and we could get the percentage of phosphorus because it's the only thing left, right? The other remaining portion is only phosphorus, right? So what does that come out to be? 59.8%. But if you want to find another way, you just simply take 30.97 grams of phosphorus over 51.79 grams and times 100, and you would get 59.8%. Do you see that? You can do it either way. It does not matter. But do we understand how to get percent composition? And the other thing that we need to make sure we understand is that when we have a pure substance, these values do not change. Our percent of lithium and percent of phosphorus will remain constant, independent of the size of the sample, whether we have 5 grams or 1,000,000 grams. Do you see that? It's going to be the same percent makeup. That's a big deal. That's the concept they want you to know in 1.3. All right, now let's go to some other things. Empirical formula says, how can percent composition data be used to determine the empirical formula of a pure substance? And then it asks, well, what is an empirical formula? And that's a great question. What is an empirical formula? So let's talk about that. So an empirical formula is a formula for a compound that gives the smallest whole number ratio of each type of atom. So we're going to see the smallest whole number ratio. Now here's an example or 3 examples of molecular compounds. We are supposed to then determine what is the empirical formula. Do you see that? And since we know the empirical formula is the smallest whole number ratio, all we have to do is reduce these expressions. So we see the ratio of carbon and hydrogen is 2 to 6, right? So all we're going to have to do is reduce that. We find the lowest value, it's 2 and 2, and we can reduce this to be what? CH3. Do you see that? That's a real easy question. What is the empirical formula of C2H6? There you go. What if they just ask you which of these is the empirical formula? And you're looking through stuff, can be reduced, not the empirical formula, can be reduced, not the empirical formula, cannot be reduced, empirical formula. Do you see that? Those are the type of questions you get. It's really that easy. If you know the definition of an empirical formula and you know how to find the lowest ratio, well, then that's easy. Most of you are in some advanced math. This is not hurting your brain. All right? Your skulls are fine. All right. So no damage to the skull. I'm not referring to any one individual. All right. So we have the next one, the molecular compound is carbon dioxide or CO2. I don't know why I said the name. CO2, right? Well, can we reduce CO2? No. So in this case, the empirical formula is the same as the molecular formula. That can happen, right? As long as so we have the molecule, CO2, it cannot be reduced, so its molecular formula is equal to its empirical formula, all right? And then last we have, this should be too easy for you by now, N2O4. Can we reduce N2O4? What can it be reduced to? NO2. And so N2O4 is the molecular formula, but its empirical formula is what? NO2. That's it. That's how did that kind of go over what an empirical formula was? Not only by definition, but in practicality, you should be able to identify, and you should also be able to write the empirical formula when given the molecular formula. All right, then it says, show an example problem for the determination of an empirical formula from percent composition. Now, there's a couple ways we can handle this problem. All right, sometimes when you're given percent composition, they tell you the total mass. Sometimes they don't. All right, here they're telling us that we have a 15-gram sample, and that sample is made up of 58.87% sodium and 41.13% sulfur. But interestingly enough, we know, and we have to make an assumption here that this is a pure substance. All right, that's the assumption we're going to make in this context, that this is a pure substance. And because we're also trying to find the empirical formula. So when we have, you're not going to try to find the empirical formula of an impure substance. That's not going to ever happen. So so because we know something about composition of elements of pure substances, what do we know? We know that their composition remains constant, independent of the size of the sample. So we could use this 15 grams. We could multiply it by 58% and get that mass, right? We could do 15 grams, multiply it by 41.13% and get a mass. Does that mean we know what the empirical formula is? No, we don't know anything. So we could also avoid doing that calculation just by doing one thing. Anytime you are given this percent composition, and this only works because it does not matter about the sample size, right? It does not matter. That stays the same. So if you just assume 100 grams, then you can use your percentage as your mass. Do you see that? Because 58.87% sodium out of 100 grams is 58.87 grams. Do you see that? Does it matter that we change the mass? No, because the composition remains constant, independent of the sample size. Do you see that? So we can avoid multiplying 15 times those percentages. All right? Could we do it if we want? If you really like doing a bunch of calculations, do what you want. I don't care. It will work. But I'm going to just show you, assume 100 grams when you see this, because you may not be given the total mass. Do you see that? So now you know what to do with that. So you're going to assume 100 grams. And then let's see what we're going to do next. Let's start here. 58.87 grams of sodium. What's sodium? What's the symbol for that? Na. All right, the morning class was just telling me all kinds of wrong. They were saying S. Y'all know who you were. All right, so 58, hopefully you're watching this video. So 58.87 grams sodium. And what we're going to do with this is we are going to convert to moles. All right, so we're going to convert to moles. These are some steps here. For each substance, sodium and sulfur. So we have 58.87 grams of sodium. We now know we got grams of sodium. Now, do you notice that I had grams right here as the given? And then what unit did I put in the denominator? Grams, because that way that unit cancels. The unit that I should be left with at the end is moles of sodium. So this would be moles of sodium. So where am I going to find the molar mass of sodium? Where would I find that? On the periodic table of elements. So what does your periodic table of elements say? 22.99 grams of sodium is equal to 1 mole of sodium. All right? And so whatever that comes out to be, you tell me. All right? It's what? 2.56. Can you give me one more decimal place? 0. All right, good stuff. Moles of sodium. Now, when you are doing these converting to moles here, do not round. Do not round, especially if the number is less than 1. This one is greater than 1, but especially if it's less than 1. Let those go out a few places. Even 4 places would be good. All right, because it can mess you up later on. I'm going to tell you why. But now we go to sulfur. And we start with, if we're assuming 100 grams, 41.13% would be 41.13 grams of sulfur. Now we use our molar mass for sulfur, grams of sulfur, which is, what's the molar mass of sulfur? Yeah, I know. It says 1 mole of sulfur. I want you to look. Some of you aren't looking. Some of you haven't been in chemistry in 2 years, and you're still not looking at your periodic table. I would be looking at it. Yeah, you know who I'm talking to. All right. So you didn't know I was paying attention to you, but I am. All right. So now, how many moles is that? 1.283. I like that you went several decimal places out there. That was very good. I like that. So what's the next thing we're going to do? Y'all remember doing this? We're going to divide each value by what? The smallest number of moles. You remember that? So what's the smallest number of moles between sodium and sulfur? Okay. What is smaller, 2.560 or 1.283? All right, 1.283. So we're going to take this one, we'll divide it by 1.283. We're going to divide this one by 1.283. And then we should get some ratio. Do you see that? And what will our ratio be? Well, this, I'll give you a hint. This one's 1. All right. There you go. I can divide where it equals 1 every time. I'm good at that one. 1.999. All right. So 1.99. If you see something like 1.999, now you can round that up to 2. If you see something like 1.5, that's going to be a problem, right? Because remember, can we have a ratio of 1 to 1.5? No, because formulas are written in what type of ratios? Whole number. So if that said 1.5 instead of 1.99, then we would have to multiply that by 2 to say it was 3. But then we would also have to multiply the other substance by 2. All right, and we see that it was a 2 to 3 ratio. Do you see that? Now, that will be on your homework, but there's also a video along with that as well. I'll make sure one's posted that has one like that. All right, so what's our ratio? It is what? 2 to 1. So 2 to 1. So 2 to 1. So our empirical formula is Na2S. We see how to do that. Is that an empirical formula? Can it be reduced? No. So that probably means we did something okay. All right. All right. Sodium sulfide, not mono. Mono would be used if it was a molecule. This is made up of a metal and a non-metal. All right. But I like that we're going back and thinking about those things. It's good stuff. I like it. All right. Are we good on that? Let's look at another one that is entirely more complicated. All right. If you thought that one was fun, wait. All right. So in this one, this is a little bit different makeup, but it's still, we have an unknown substance. All right. CXHX, we don't know what that is. We want to know what is the empirical formula of this compound. What we know is we have a 1.50 gram sample of a hydrocarbon. So a hydrocarbon, you're not going to believe this, is a compound made up of carbon and hydrogens, and sometimes oxygen. So here we have it. It's just made up of carbon and hydrogen. Now, when hydrocarbons react with oxygen, we call that a combustion reaction. All right? It's a special type of oxidation reaction. You all remember talking about that? It's a special type called a combustion reaction. So anytime we have a combustion reaction, the products are going to always be carbon dioxide and water. Now, I'm giving you that stuff right now, right? Right now, I'm giving you that. All we're asked to do is to determine what is the empirical formula of that hydrocarbon. Now, in order to do that, we're going to have to be a little bit fancy, all right? Because we don't have just percent composition or mass here to deal with, right? We have the mass of the products. Do you see that? We have the mass of the products. We don't have anything else to work with. So we're going to have to determine, based off of the law of conservation of mass, that we can come up with this ratio. All right, let's look at this. So we're going to start off with 4.40 grams of carbon dioxide. 4.40 grams carbon dioxide. And what we're going to do, if I wanted to know how many, what the number of moles of carbon were, would carbon dioxide be a good substance to use? And then why or why not? Or would water be a better substance to find than moles of carbon? Well, no, we're not. Don't go into that right now. No. Okay, let me ask you this. Does carbon dioxide have carbon in it? Oh, so you could stand to reason that you could determine the number of moles of carbon. Yeah. All right. Does water have carbon in it? You're not going to find any carbon there. Do you see that? So that would not be a good substance to determine the percent or the number of moles of carbon. So we want to find the moles of what? Carbon. Why is carbon dioxide a good substance to use for that? Because it has carbon. How about that? All right. These things I'm connecting, you're like, wow, it's deep thinking. All right, it's not really. So now what we're going to do is we're going to have to convert carbon dioxide to what? Moles. Grams of carbon dioxide to moles of carbon dioxide. Now, that means I need to know what? The molar mass of carbon dioxide. I don't know what the molar mass of carbon dioxide is. I have no idea. It is 44.01 grams of carbon dioxide is equal to 1 mole of carbon dioxide. Does that say carbon? No, it says carbon dioxide. I want to know the moles of what? Carbon. So this is something we learned in Unit 1.1 and 1.2 is in 1 mole of carbon dioxide, it is equal to 1 mole of carbon and what? 2 moles of what? Oxygen. Now, we only need to know how it relates to carbon. So 1 mole of carbon dioxide is equal to 1 mole of carbon. All right? And yes, you do need to show, even though it's not changing your numerical value, you need to show that, right? Because that shows you know the concept, right? How you're getting that. So now we do this. What does this come out to be? I don't know if my answer is right or not. 0.0999 moles of carbon. All right, so now we're going to do the same thing. We need to figure out the moles of hydrogen, right? Just like we were calculating empirical formula before, we figured out moles of each substance, and then we did what? Divide the smallest value into the larger value. So remember doing that just a second ago. So that's exactly what we're doing here. Now we're going to find the moles of hydrogen. What substance makes the most sense to find the moles of hydrogen? Water. How about that? Because water contains hydrogen. So we start with 2.70 grams of water. And then we need to know the molar mass of water. (18.02 grams of water is equal to 1 mole of water. This is the trick. This is the trick. 1 mole of water equals moles of hydrogen. How many? 2. Y'all are a go. Look at that. Look at that. Y'all might not need to rewatch this video. Y'all are so good. All right. So what do we have here? What do we get? Say again. 0.299. We don't have another decimal. All right, let's go with that. Moles of hydrogen. Now, what is the smaller value? I know it's hard, right? Carbon. All right, 0.0999. This is equal to 1. 0.0999. This is equal to what? 2.999, which is what? 3. So our ratio of carbon to hydrogen in the empirical formula is 1 to 3. So carbon, 3 hydrogens. The empirical formula is CH3. We see how to do that. Woo, that's fun. All right. Let me say it for my morning time fans. Holy smokes. All right, that's pretty good. All right. So that's all I have there. I'm going to stop this video at this time, but I do want to say thank you for watching. Please like and subscribe.